we're going to start delving now that you're complete pros at programming the beta, as I'm sure you're totally kind of good at it. We're going to start going inside some of those boxes that we talked about the last time. Remember, there was the register, there was the register file, there was the multiplexer or the selector. That was the same item, two different words. And in particular, there was this wonderful unit in the inside that did calculations, and it was called the arithmetic logic unit. And so today we're going to talk about how that sort of most essence of essences inside the computer works. And I know that you guys have had some math stuff, so some of this may not seem that bad to you. First of all, what are we talking about? We're talking about this thing right over here. It takes the A and the B and takes some sort of an opcode from the instruction stream that is decoded. In other words, there's going to be some logic between this opcode and the command to the ALU saying what function to do, and the ALU is actually going to do the work, and it's going to do things like adding and subtracting, and, or, XOR, stuff like that. Now, we need to think about a couple of different things. First of all, there are things in order to add. How do we add numbers? There's also other architectures which have to do with how to multiply. And despite the fact that this thing here says that we're going to learn this now, we're actually going to put that off a little bit, and it'll be an optional thing. If you guys want to learn this on your own, you can take a look at the textbook that was bought for this course and learn how a multiplier works. We're going to come back to this a little bit later on in the course when we talk about pipelining, and we'll show a particularly simple kind of multiplier. But for now, what I really want to concentrate most on is adding, because I think the sense that I'm getting is that the course is going just a little bit too fast, right? And so I'm going to slow down just a little bit here, and we're just going to handle add. But in particular, we're going to talk about how to make an adder that's fast, because if you remember, we wanted the data to percolate through as quickly as possible so that we could clock those registers down at the bottom again without having to wait too long for the data to percolate through a second time. We're going to see that there are trade-offs between how fast a particular architecture is for the ALU and how big it is, how much space it takes up. Okay, in general, it'll be possible to make an ALU that's very small but very slow, or very big and fast. And of course, space has a lot to do with cost, because the larger the ALU takes up the area of the chip, the bigger you have to make the chip, and thus the more it costs. And the reason is not that the bare materials cost very much, but the bigger the chip is, the less likely it is that everything on the chip will be perfect, and thus the yield of how many chips are good goes down, and thus the cost goes up. Alrighty, let's get started. Here's that horrendous picture that I showed you the last time of what an ALU for 4 bits looks like. And in particular, this is a very old ALU, sort of a very famous one, which was built in a single chip called the 74181. And in the old days, we used to actually have students build all kinds of processors and stuff out of this chip. But if you take a look at it, what it does is it takes a whole bunch of symbols here. It's very hard to see from the back, but don't worry too much, that are called A. A0, A1, A2, A3. And it takes another set of inputs called B, B0, B1, B2, and B3, and it passes them through a bunch of logic and comes out with an answer, which is F0, F1, F2, and F3. And we're going to talk about how that logic works. I think you'll see some similarities to the discrete math course that you just took. The first realization that you may have, if you think about this at night, is, you know what? This isn't hard to do at all. In fact, for every 32-bit number A, and every 32-bit number B, and every ALU function, which is going to take a couple bits. Like, how many bits could it take to do add, subtract, and, or, XOR, all those things? Let's say, I don't know, 5 bits, okay? So there's 32 bits here, and 32 bits here, and let's say 5 bits here, for a total of 64 plus 5 is 69 bits that go into here, and 32 bits out. This is simply a table that has 69 bits in and 32 bits out. And that means that I can describe exactly what that function is by having a table like this, and the output is going to be 32 bits wide. So every entry in here is going to be 32 bits wide. And as input, I'll have all of those bits that go in there, the 69 bits going in there, and that will control how far into the table I look, and out will pop the answer, n, that I'm trying to get. Now, what's wrong with this thing? Well, 2 to the 69, and over here I said 2 to the 70, is a big number. How big of a number is it? It's a really big number, okay? And so, therefore, 2 to the 10th is approximately 10 to the 3, right? So let's say this is 2 to the 70. What is that then? 10 to the 21. What's 10 to the 21? 1 with 21 zeros, right? That's a lot of zeros, okay? And therefore, the number of rows in this thing would be 10 to the 21, or on the order of 10 to the 21 rows, and this table would be much, much too big. So even though we could implement this thing as what's called a lookup table or a memory, notice the architecture here is simply that of a memory, it's impractical to do that, okay? But theoretically, at least, it is what's called a combinatoric logic function, which means that the output is purely a function of whatever the combination is of the 70 bits that go into figuring out how far down in the combination table we're going to look. Okay, it's just a pure map from in to out with 70 bits in and 32 bits out. So that's not good enough. So instead, what I want to do is, instead of trying to do the whole thing in one table, let's actually try to build it up from the bottom. And I think that you'll find that this is very familiar, and it'll be a little bit of a break. And it involves taking a look at one bit at a time. And I believe in just, is it true that you guys have all done a adder of some sort? Okay, with ants and ors? Okay, good. So this is all going to be easy. What? It was on the test. Okay.
So we don't know if we've done it right.
So you don't know yet? Oh, and the finals haven't been turned back yet? Oh, okay, well, you haven't looked at, oh, that's interesting, okay.
We don't want to ruin our day.
So let's just take a look, not at doing 32 bits of ALU, but only 1 bit of ALU. And in particular, if I have a 32-bit number that ends in 0 like that, and another 32-bit number that ends in 1, I would like to sum them. Actually, let's have it not end in 1. Let's just sort of say it goes on and on and on. Then the sum of 0 and 1 is going to be 1, right? And there's going to be other stuff here and other stuff there, except I need to be a little bit careful because it's possible that over here I had a sum, 1 and 1, let's say, which had a carry, of course, that came out of here. And so this is really 1 plus 0 plus 1, which is 0, and a carry got generated out of here. So this is nothing more than the binary version of adding numbers that you've known how to do since grade school. So there's the idea of I need to sum together A and B sub I, because this is, here's A and here's B. So this is A sub I, the bit I of A, and here's B sub I. But I also have a carry in and a carry out as well as sum sub I that comes out of here. Okay, so there it is. A single bit slice of a adder like this, and for now I'm going to concentrate on just adding because it turns out that all of the ALU functions that we're going to do, add is sort of the most difficult of them. Okay, and or, stuff like that are actually pretty easy. A sub I comes in here, B sub I comes in here, carry in goes in here, carry out goes out here, and the sum bit pops out down at the bottom. We can describe this with a map exactly like what I just showed you over there, except luckily now we have far fewer than 2 to the 70 bits. How many bits of input do we have? 1, 2, 3. 3 bits of input. How many bits of output? 1, 2. So with 3 bits of input, the number of rows that I have to describe the function is 2 to the 3, or 8 rows, starting at a row with all zeros in it and just counting through all the combinations until a row with all ones in it. And so I can say, okay, if A is 0 and B is 0 and the carry in is 0, then the sum is 0 and the carry out is 0 also. Fine. If B is 1, the sum becomes 1, but we don't carry out. If A is 1, then the sum becomes 1 and we don't carry out. And if carry in is 1 and the other two are 0, it's exactly the same thing. Right? Now, if 2 of the input bits are 1, then the sum is 0, and we carry out. Here's 2 of the input bits are 1, the sum is 0, we carry out. 2 of the input bits are 1, the sum is 0, we carry out. And the final case that we haven't covered is, what if all the bits are 1? And in that case, the sum is 1, because 1 plus 1 plus 1 is 1. Right? If I tell that to my 9-year-old, he'll laugh at me, right? With a carry out of 1. Okay, so we've handled all of the cases. Now, what you realize when you do this is that you could combine a set of full adders the same way that I just showed you there, by putting them in a chain like this, where the least significant bit is over here on the right-hand side, where we traditionally draw bit number 0. And the most significant bit is on the left-hand side over here. And if we're just summing together 2 n-bit strings, what carry in do you think we should feed in on the right-hand side here? A 0 or a 1? 0. Okay, great. And what would the carry out of the left-hand bit mean? So let's say I fed in 32 bits of A, 1, 2, all the way to 31 and 32, and also B, and I got a 32-bit number out of here, and I had 32 full adder 1-bit slices. Well, what would it mean for the carry out to be high?
Isn't that going to depend what our sign is?
That's absolutely right. So if the numbers are positive and you get a carry out, what does it mean? The number got too big, right? Because it is possible to add 2 n-bit numbers that are positive and end up with a number that no longer fits in n bits, right? It can fit in n plus 1 bits. And so the question is, well, what do I do with the extra bit that overflows out of the side? It turns out that if you use the 2's complement notation, which if you haven't done it before, you're going to do it in a future section. You did it yesterday? Okay, great. That the carry out means something a little bit different. Okay, and in general, the rule is with a simple adder like this is if the carry out agrees with the sign bit, then no overflow has happened. So in the case of a positive number, the sign bit is 0, and then you expect the carry out to be 0 also. However, if the sign bit is 1, meaning the number is negative, and you add 2 numbers together, and you do not get a carry out of 1, then something's wrong. It means you've overflowed going negative. Okay. So anyway, that's a sort of general issue that we're going to have to figure out how to deal with overflow in these summations in the ALU. The second problem we have to deal with is a performance issue, and I want to begin to talk about it right now. And it's a performance issue because, well, this is really slow. Why is it slow? Well, these 3 bits, let's say, are applied simultaneously. The 0 is applied here. A sub 0 and B sub 0 are put in here. And after a short amount of time, this produces the sum sub 0 bit and the carry out sub 0 that comes out of here. This full adder over here gets A sub 1 and B sub 1, but it can't really begin to do its work until the carry in is generated going into there. So it has to wait for this guy on the right to finish its work before it can start. And furthermore, the one to the left of that can't start until this one here gets done figuring out what its C sub out is going to be. And so on, and so on, and so on. And so the longest path through this circuit is from these bits over here through this long chain of 32 full adders, finally to an output over here. And so the longer the word length of this thing, the slower the operation is going to be. Not for these least significant bits. Those get figured out pretty quickly, but it takes a long time for the carries to ripple all the way through here until they finally get to the end and pop out.
That's in the worst case.
That's in the worst case, yes.
Best case,
You're
not take much.
absolutely right. And in fact, if you add 1 plus 1 and just get 2, you're only going to use these 2, and the rest of them are going to be able to come up with the right answer very, very fast.
You can have a 32-bit number or 31-bit number, and still somewhere along the line you can start the 4th adder without having gotten the results from the 3rd adder.
That is also true, and we're going to talk about just one of the many ways that you can do that. In fact, that's sort of the later part of the lecture here. So, but in this simple case of just the ripple carry adder, in general, first of all, it has 2 issues. One is that it's highly dependent on what the numbers are that you're trying to add. If the carries only happen on the right-hand side, then the adder will be fast. But if the carries are required to go all the way through, like, having an odometer on a car, and it says all nines, right? And you go over that last mile, right? And that last one turns the next 9, and that 9 turns the next 9, and that 9 and it never quite, goes all the way to 0 because it's a little bit skewed. That's kind of how this full adder system works, okay, the ripple chain, but it takes a long time for it to carry over. Yeah.
But wouldn't you have to check all the way along the line anyway, in case there were, say, in the n-1
Sure.
get 2 1s?
Absolutely.
They were a whole bunch of zeros on both ends in the middle.
So then the question is how do you know when you're done, right? And of course, the safe thing to do is you wait for 32 times, however long it takes one of these guys to work, and then you know that you're done. Or maybe you build some extravagant circuit to find out when you're done. And maybe you actually clock your computer at a different speed depending on how long it takes the adder to get its job done. In the later part of the course, we're going to talk about different ways of clocking the processor, either slower or faster, in a data-dependent way. So sometimes adds are easy to do, sometimes adds are hard to do. Why not take advantage of when they're easy and clock the machine faster? Okay? It's something that's not usually done, but in the highest performance systems that are out there, they are starting to do it now. Okay.
Did I understand to say that what you're saying is that the computer will actually, on the fly, change its speed?
Absolutely
Go
right.
from a 300 megahertz to a
Absolutely right.
900 megahertz
Right.
or something?
From clock cycle to clock cycle. In fact, we're going to look at systems that have no clock per se, but, well, actually, this system here does it too. This has the Intel speed step blah, blah, blah thing, right? But that's supposedly to save the batteries, right? That when it's sitting there and Windows is doing nothing, then it slows down or something. Or when the battery runs low, then it slows down. You can actually build a system with no clock at all, where the adder, and I'm giving a little hint here, they're called self-timed systems, where in addition to the data that goes into a ALU like this, you actually have a start pulse that says, okay, go. And what comes out of the ALU is not only the answer, but a finish pulse saying, I'm done. And as soon as that's done, then the next piece of the circuitry that depends on the data that this thing spits out is triggered saying, okay, you start. And then these little start pulses chase each other through the circuit and actually loop back and start all over. And the system has no clock at all other than these start pulses going around and around and around. Okay, and so we're going to talk about those during the end of the course too, these self-timed systems. They're a really wonderful thing to think about. They're not used very much, but there are reasons for that too. But we can't talk about that now because I'll be here for half a day. So let's try to figure out now, first of all, exactly how to build this full adder bit slice. And let's also try to see if we can't see hints as to how to make this thing a little bit faster. And some of you know where I'm trying to go here, but it'll be fun anyway, okay? Let's take a look at the carry out. What is the function of the carry out? You've all had your math class, so I think that you can read this. A product in a logic notation like here means and a plus sign means or, right? So this means C sub I, A, what sub R mean? Not, okay. C sub I, not A, B is the and of these three things. And so that would correspond to, let's see, C sub I, not A, B, this term right here. So this is the row in the truth table here where C sub I is true, A is false, B is true, and C sub O is 1. So by putting this, what they call a product term in here, if this is true, then because this is this or that, this will cause C sub O to be a logic 1. And so I have 4 product terms that are ORed together here, okay? And so this is called the sum of products form. And each one of these terms, since it's a AND of 3 inputs, corresponds to exactly one of these rows. And so those 4 terms correspond to the 4 ones, 1, 2, 3, 4, that I have in the truth table right here. And so this should be kind of looking pretty easy right now because you've seen it before. Okay, but what really is CO? Aside from the logic, what the carryout is really telling us in English is the carryout is a 1 if 2 or more of the inputs are 1. Okay, because that's really when we want to generate a carry coming out. If 2 or more of these 3 bits, the bit A, the bit B, carry bit, these 3 bits here, if 2 or more of these are 1, then we generate a carry out. So that's sort of an easier way to talk about that.
It would have been simpler if you switched the CO and the S rows, because that's simply the binary sum of the 3 ones or the 2 ones on the side. Switch the CO. and
If I switch these 2 rows here,
Right, and then reading the 2 digits together is just the binary sum of the ones on the side.
of the ones on the side, I don't know what you mean by...
The CI, the AA.
Oh, okay, I guess that's absolutely true, isn't it? Cool. Good. And in fact, that's because you're adding, right? And so that kind of makes sense. Right. So you're counting the number of ones, so this is what you're... No, it's, look, it's neat to me, okay? So you're absolutely right. The CO should have been on the left, and then it would have made some more sense. So how do you actually simplify the logic of these ands and these or terms? And you guys have been through a discrete math course, and you did it the hard way. Okay, and the hard way is basically you kind of look at the thing, you say, well, I can distribute and over or, and I can also distribute or over and, which is kind of funny. And I can manipulate these symbols here and try to make something more simple than it was before. What I'm going to show you now is a graphical way to do it, which is far more straightforward than the way that you've done before, and which you'll have more practice in the recitation that's going to follow this class. And what it's called is called a K-map, and K stands for Mr. Carnot. It's, I think, K-A-R-N-A-U-G-H, who was a bachelor student at MIT and did this for his bachelor's thesis back in the 1950s. Okay? And ever since then, poor designers have had to learn it. Here's the idea. Instead of showing the table like this, or even with the lines switched like that, which would have been a great idea, we rearrange the order of these bits here to more closely show which ones and which zeros correspond to changes in the input where only 1 bit is changing at a time. So here's the idea. I'm going to label a table here of 8 bits. Okay, here's 8 bits that are going to be for S. Here's 8 bits that are going to be for S. These are the same 8 bits as there are over here. Okay? And these 8 bits here are for C sub O. Those are the same 8 bits as there are for there. You can check. There's 4 ones over here, and there's 4 ones over here. So that's the same. Except I'm not going to list those bits in a table using sort of counting order for the 3 inputs. Instead, what I'm going to do is I'm going to lay them out graphically so that the order of the inputs is given in this graphical form where I read it in the following way. In these 2 columns here are going to be the 4 cases where A, the input A, is 1. This column here and this one here. And I'm going to denote that by saying A inside of these 2 bars. Okay, so in here A, down, both A is 1. And these 2 columns over here, B is going to be 1. It's cool. And in this row over here, C sub I is going to be 1. That's pretty neat too. Now what's the characteristic that a kind of checkerboard like this has? Well, it has an amazing thing. First of all, if I'm in any square, this corresponds to A equals 1, B equals 0, because I'm not in the 2 columns with B, and C sub I equals 1. That's this place here. If I move in this direction, how many of the input bits change? I go from here to here. Only 1. If I go from here to here, how many change? 1. Here to here, 1. So whenever I move across a neighboring to a cell that's right next door, across a border, only 1 bit will change. Furthermore, this isn't really a square grid like this. It's actually a toroid in that this edge here is the same as this edge here. So if I'm going over here and I fall off the bottom, what I really mean is that I come back around and come to the top here. Now that doesn't matter so much when there's only 2, because going around this way is the same as going back and forth here. But let's say that I'm over here. I move like this, 1 bit will change. A changes from 0 to 1. Here, B changes from 0 to 1. Here, A changes from 1 to 0. And then I go 1 more, come around, come back around to this side, and what has changed? B has changed from 1 to 0. And in fact, the way that the bits change as you go around and around here is, and you may have learned this, called a gray code. Only one bit will change at a time. And so this has the characteristic that the axes are labeled in gray code. It's a fantastic device for simplifying logic expressions. In particular, I just talked about that, we can extract in the K-map certain types of functions. First of all, let's take a look at the function AND. You guys know all about AND in the usual truth table where A and B are given as 0, 0, 0, 1, 1, 0, 1, 1. But now do it in K-map form. So here's where A is true here in the middle. And here's where B is true over here at the bottom end. And you see that an AND is nothing more than if A is true and B is true, then the output is 1. So again, it's a gray code. Both are low, one's high, the other one's high, and then the first one is low, and then going back to both of them are being low. So that's the description of an AND gate in K-map form. Here's the description of an OR gate in K-map form. Now, unfortunately, when I first did this slide in PowerPoint, I didn't know how to make arcs. So most people draw and let me use my hand here to do it. The usual way you draw an OR gate, and you've seen this before, is like that, okay? So it's kind of got a sharp thing here and a smooth thing in the back here. But that's the best that I could do back when I first did this. And I was trying to learn PowerPoint. Not very well. But anyway, you see, of course, the OR is true when A or B are true, or when both of them are true. There's also XOR. That's an exclusive OR. And typically the symbol for that looks like this, with an extra arc on the back of it. And it has a K-map form that is very interesting in that it looks like a checkerboard or a chessboard, where it goes dark, light, okay? And whenever you see things that look like a checkerboard, the first thing that should go into your mind is, this looks like XOR. And why is that? Because XOR has this incredible characteristic. If I have XOR of a whole bunch of bits, and here's an output, and let's say that I put in a bit string, right? 0, 1, 0, 1, 0, 1. What is the XOR of all those bits? Somebody said 0. Is it 0 or is it 1? What does XOR actually do?
Gives you the odd or the even parity.
That's absolutely right. It measures what's called the parity of the input here. It's counting how many ones there are, okay, and it's seeing if the number of ones is odd or even. Now, is the number of ones here odd or even? Odd. So what is the XOR of all these things going to be? Well, you can think about it in the easy case where there's only 2 bits. Here's another one where it's odd. What's the XOR of 0 and 1? 1, okay. So that's 1. But look at what takes place here. What happens if I change any of these bits? If I change this one from a 0 to a 1, what's the output going to do? Switches from 1 to 0. And in fact, it has this great characteristic that it is sensitive to a change on any single input with a flipping of the polarity of the output, because it's checking for oddness or evenness, and whenever you add a 1 or subtract a 1, if it was odd, it switches to even. If it was even, it switches to odd, so the output will change from a 1 to a 0. And that's why when you look at a K-map of something that has XOR in it, you always see this checkerboard or chessboard type thing where it goes 0, 1, 0, 1. Why? Because in the K-map, as you move from one square to the next, exactly one input is changing. And you know that the XOR of something where one input changes switches from 0 to 1. So it has no choice but to act like this.
So if we had 3 or 5 or some odd number of wires coming into...
We're actually going to look at that.
Okay.
Then you'll get to see what it actually looks like. Okay?
This is the light switch circuit.
This is exactly the light switch circuit. If you have 2 lights, excuse me, 2 switches for 1 light, right, or even 3 if you set it up with 3, and the one at the top of the stairs, works one way, and the one at the bottom of the stairs works the other way. They work as an XOR. So either switch can always change the state of the light, which is exactly what you want to have work. How many people actually know how to hook that circuit up? Anybody here know? Small aside here. Okay, here's the battery. Here's the light bulb. Actually, how many people know the symbol for a light bulb? Or the symbol for a battery? And which one is plus and which one's minus? That's okay. Now let's say that you go ahead and you hook this up here. So clearly if I hook this wire to here, the light goes on, right? How do I hook up two switches to act as XORs? There'll be some way to do it. I'll give you a hint. You can use a switch that has what's called two poles on it. So in other words, if I put it up, it goes to this path. I put it down, it goes to the other path. Anybody want to take a guess?
And there's a switch at the other end, pointing back.
This, okay. It actually doesn't matter if you cross the wires or not, but the switch at the other end is the right answer. It looks like that. So if this one is, let's say this one is up, and this one is down, and the light's off, but if you turn this one up, then the light goes on, right? But if you don't turn that one off, you turn this one on, then the light goes on. Whichever one you switch, the light will change from one thing to the other.
What happens if you put it in the
And what about a third switch? I'll leave that to you. Okay? This isn't a class in wiring, so. I'll let you all have fun in your houses, and when your houses burn down, it won't be my fault. Or maybe it will. Okay. So now let's look at a two-dimensional K-map with three input terms and understand the product terms. Here we have four product terms. Each of them has three inputs that it is sensitive to. C sub I bar A, B. Now where is C sub I bar A, B on this thing? C sub I is not true. That's up here. Okay, here's the place where C sub I is true. Here's the place where C sub I is not true. So C sub I bar, A should be true and B should be true. So we come along here. That one. Okay, so this one is the one that this term over here is responsible for generating. When all these three inputs satisfy the condition that we give it, this being low, this being high, this being high, this term, quote unquote, fires. In other words, the AND of these three things is a 1, and it is responsible in this OR gate of these four terms for holding the output C sub O high, for making this be a 1. And we indicate that by saying, okay, it's 1, and we put a circle around it, saying that this circle corresponds to this product term right here. And you'll notice that there are four circles in this picture here, and there are, in fact, four product terms that I've drawn right here. So what's this one here? This is C sub I A B bar, right? C sub I A B bar is right here, or not B is the other way to say it. This is a bar here on the top. So that's this term here. And you can go through and you can see that each of the circles here corresponds to exactly one of the product terms that we have here. So that's nice. But it turns out that we can do a simplification on this K-map, which is identical to the very difficult simplifications that you guys did in the discrete math course. We can make these circles bigger than one square. What we can do in particular is I can take these two ones that are near each other that used to have a circle on each one, and I can circle both of them. Now what does it mean to circle both of them and to make only one product term out of this oval here instead of the two product terms that I used to have? Let's only pay attention to this one over here on the left. Well, it used to be that I had one term that was dependent on A, B bar, and C sub I, and another term that was kicked off by A, B, C sub I. And now I circle both of those, and what I'm really doing by making that bigger circle is I'm saying I don't care if B is a 1 or if B is a 0, as long as the other two inputs to this system satisfy A is 1, C sub I is 0, it doesn't matter. The output's going to be 1. Don't care about B. In other words, I'm going to extract from this thing the fact that it's insensitive to B. So this term is just A C sub I without a B. This one over here is what? Is B C sub I without an A. And this term over here is what? A, B without a C sub I. And so if I look at that, then I say the answer, the simplified version of this of this function is a c sub I or ab or b c sub I. And that would be a result that would be very difficult to figure out by hand. Now, you could do it, okay, but it would take a lot to finally see the symmetry in all of this stuff. And if you think about it a little bit more, what is the logic here actually saying?
And at least two of these have to be +1.
You got it. That 2 or more of the inputs need to be 1. And this tests for these 2 inputs, these tests for the other 2 inputs, and these tests for the other 2 inputs. You have 3 wires. There's 3 ways to test for 2 of them being 1. And so you just OR up those 3 cases. Okay? What's wonderful is that this graphical technique allows you to simplify any sum of products form, anything where you have the OR of a bunch of ANDs, by sort of coalescing smaller circles into bigger ones. Now, there's a few rules. The first rule is you can't make bigger circles whose size, whose number of terms they enclose, number of ones they enclose, is not a power of 2. Now, why is that? Well, when I merge these 2 ones by changing it from a circle that's as big as a 1 to a circle that has 2 things in it, I eliminate 1 variable. Now, let's say that there was a 1 here too. Let's just sort of pretend that there was a 1 here, and you'll actually get more practice in the recitation doing this, so I won't do this on the board now. But let's just say that this was a 1. I could have circled all 4 of these with a big term. And what would that term be? A. I don't care about C sub I. I don't care about B. It's just going to be A. So again, you always have to grow them by a factor of 2, because doing that says I'm throwing out the dependence on one of the inputs. And that's exactly what is going on here. You can't make one that's, 3 big, okay, by saying, well, this is 1 term. Because there's no easy way to describe what that is. Okay, it's just a way of knocking variables out of product terms. Second rule you need to know is that, let's say that there was a 1 here and a 0 here, then you could have coalesced this one over here off to the right with this one over here off to the left. And again, you'll have practice doing that as well.
And you only circle the ones of that?
Well, there's actually 2 ways to do this, and in the recitation, I think you'll get practice doing it both ways. If you circle the ones, it has to do with the sum of products form, which is the OR of a bunch of ANDs. Guess what it is if you circle the zeros? Product of sums form. Okay, so you can do it the other way.
Either way, you're just doing one of them. You're looking for groups.
You are
of-
choosing one or the other, yes. You are not doing both. Now, I do not want to get too obsessed with K-maps, okay? So when I went to school, back in the Stone Age, right, we went nuts with these things, okay? We did 4-dimensional K-maps and 5-dimensional K-maps, and there's, so this one has 3 inputs, right? One with 4 inputs looks like this, right? And has 16 possibilities of the 4 inputs, right? And so if it's A, B, C, and D, this is A, this is B, this is C, let's say, and this is D, right? That's one way to do it, okay? But now the question is, well, what if there's 5 inputs? Well, the answer is that you draw 2 of these, okay? This is back when I went to school, right? There's 2 of them. And then you kind of draw this like little dotted line saying that they're connected to each other, right? Because they are. And there's a difference of exactly 1 bit between this one and that one, and you call that E. Okay? And then if there's F, then there's 4 of them, right? And then, it gets harder and harder and harder to do. The real thing that's going on here, it turns out that we're lucky that we can draw these and imagine in our mind that this surface is the same as this one, and this one here is the same as this one here, but we can't go beyond that, right? What's actually going on is that all of these things are really what's called a hypercube, a binary cube that is going into more and more dimensions, and each time we add another input to this thing, we make the cube bigger and bigger and bigger, and the only difference is that we've managed to get away with doing 4 things in a plane, just because in our minds we can say this surface is the same as that one. But to really do it right, you just have to think that every time you add another bit of input, you add another dimension to this hypercube. And the software programs that do all this work for you in a split second, okay, do it in that fashion. They think about, the software thinks of these things in terms of a hypercube. The reason I don't want to waste too much time on that is that no designer ever does this anymore. Okay, the software that does this stuff is built into every CAD package on Earth. Okay, at the lowest. This is like the easiest thing that they all do, and so to simplify these things really isn't part of what we need to do. But it's good because you get to understand how to build certain things. Okay, how about S? So we just did C sub O. How about the sum? The sum is equal to 1 if what? What does this look like, guys?
Parity.
Looks like parity, looks like XOR. That's absolutely right. It's a checkerboard. And so in order to generate this, I have to basically put a circle around every single one of these ones, and then I have to ask myself the question, can I coalesce them into bigger terms? And the answer is no, I can't. Okay? So I can't make a sum of products form that's any more simple than having 4 terms, which we saw at the very start, which take into account the individual rows where S is 1. Because this is basically saying, is the number of ones in the input odd? That is what S is. And so it's exactly the parity function. All righty. So parity, however, does not mean that you can't build a circuit to simplify things anyway. So what am I really trying to say here? Sum of products form is effectively saying that I'm going to build my logic in the following way. There's going to be an OR gate, and feeding into that is going to be a bunch of AND gates. And feeding into those AND gates are going to be various connections to inputs. Okay, and I'm drawing this in a very messy way on purpose, because you're going to see what I'm going to do. And I'm not going to worry about what gets hooked up here, but here's the inputs A, B, and C. Here's in. And I'm going to take A, B, and C, and I'm going to form wires that correspond to A, B, and C, and I'm also going to take the inverse of A, B, and C. These are NOT gates. And I'm going to take, this is going to be A bar, this is going to be B bar. That's a kid's book too, B bar or ba bar, I don't know, different. This is C bar, here's C, here's B, and here's A. Okay, so the first thing I'm going to do is take all the inputs and form their complements, the knots of them. And then I'm going to have this matrix where I can hook up some wires to each other. And I'm going to choose certain ones of A bar, B bar, C, and C bar. And I don't know which ones I'm going to pick, but in each one of these, I'm going to form a product term, the AND of those things. And then I'm going to take the product terms and I'm going to sum or OR them together here, and I'm going to form the output here. And what we've just learned, first of all, and which I think you learned in the logic course that you took, is that this structure of the inverse, the AND, and the OR can do any function on Earth. Okay? But the question is this the most efficient way to do the function? Well, it seems to be the fastest, because after all, it's only 3 levels of logic, right? And how can you beat something that takes 3 stages of logic, no matter how complex it is? Well, except for the parity function. If you try to implement the parity function like this, of 3 inputs, you're going to need 4 gates. If you add another input, a 4th input, how many AND terms are you going to need? Parity of 4 inputs. Well, there's 2 to the 4 combinations, right, which is 16, half of which are going to be 1, and you can't simplify it. So how many gates do you need here? 8. Okay, great. 5 inputs. 16. 6 inputs. 32. 7 inputs. 64. The number of AND gates here begins to grow really fast. Okay, and that's awful. And it turns out that this is an exponential growth in the complexity of the circuit versus the number of inputs to do parity. And that sucks, because often we want to take the parity of a 32-bit word. And God forbid we should have a 32-bit word with 2 to the 32 over 2 equals 2 to the 31 AND gates. First of all, that is 2 billion AND gates. Now, integrated circuits are nice, but 2 billion AND gates is still a whole lot of AND gates. Okay? And you know what's even worse than 2 billion AND gates? Two really awful things. A lot of those AND gates are hooked up to the same wires. And it turns out, and we're going to talk about the physics of this, that the electrical characteristic of these AND gates loads the wires just a little bit. Sensing the 1 or the 0 on a wire involves transferring a little bit of charge into or out of the AND gate. And if there's 2 to the 31 AND gates with a lot of them on the same wires, there's a lot of charge that needs to go in and out. And what does that mean? A, the amount of power you need to do that is very large, and B, it's really slow. Because if you supply the charge at a fixed rate, the amount of time it takes to charge them all up is a long time. Even worse than that, we have 2 to the 31 wires going into this big OR gate. So it's an OR gate with 2 to the 31 inputs. I've never seen an OR gate like that, but if there was one, it would be incredibly slow. Again, because it would have to consider all of these things, and in determining what the output should be, there would be a lot of charge that would have to get transferred to figure out whether one or more of these is in fact high. Okay, so sum of products sounds like magic, and it is for some functions, but not for all. And the wonderful thing about the adder is that it gives us an example of one function in particular, the parity function, for which sum of products is absolutely the worst thing that you could do. So what's a better thing that you could do? Use XOR gates. Because XOR gates sort of have an intrinsic ability to do parity to begin with, and if I have a desire to do parity of n bits, what I'm going to do, let's say I want to do a parity function of 8 bits. I take a set of XOR gates like this, each of them with only 2 inputs. And now what do you think I should do with them? So let's think about this. This output is a 1 if the number of 1s here is odd. This output is a 1 if the number of 1s here is odd. If I have an odd number of 1s and an odd number of 1s, how many 1s do I have? Odd or even? Even. So what should I do to these two things to find out if the number of 1s in all 4 of these is odd? Put another XOR gate. And this tells me the parity of 4 things. Because this can be 1 if one or the other of these is 1 but not both. And if one of those is 1s, it means that one of these is odd but not both. Right? So either both of these are 1 or none of them. And one of these is 1, so the number is odd. And so this is saying odd. This is saying odd. Of course, I can do the same thing here. And then I can take these two things, of course, and this tells me whether or not I have odd parity of 8 inputs. And so this is a tree. And it's a tree that is not, by any stretch of the imagination, sum of products form. It's not that I do an inversion and then an AND and then an OR. And yet it's only 3 levels deep. And it can handle 8 inputs. Draw me the sum of product of 8 inputs. 2 to the 8 is 64, right? So I'm going to have I'm going to have 32 AND gates and an OR gate with 32 inputs, which is a huge structure compared to this one with 1, 2, 3, 4, 5, 6, 7 parts in it. Much smaller and much faster too. Okay, so the big message here is that Carnot maps and sum of products is good, but don't get fooled into thinking that that's all there is. Often there are other forms which are in fact better, depending on the function. So anyway, this is just saying the same thing here, that a tree structure here of an n input tree here has order log n levels. The propagation in general takes order log n time to get through this thing here. And as I hope you guys all know now from your math class, it's order n parts. Why is that? Because there are exactly n over 2 parts here, n over 4 parts here, n over 8 parts, et cetera, you sum together n over 2 plus n over 4 plus n over 8, and you get n minus 1, right? And n minus 1 is order n.
the simpler way to see it is that for each NOR gate, you're knocking off one of the wires. So if you start with n wires, you have n minus 1 NOR gates, and you're going to have.
Okay, yep, that is absolutely true too. Okay, good. So we see how we can implement sum using a parity tree like this, and we see how we can implement the carry out using a sum of products form that we can simplify by using a K-map. But still, we're left with a adder structure that's a series chain of these things and kind of slow. So let's talk about exactly what's going on inside of this adder and see if maybe we could sort of speed things up a little bit. In other words, is it really true that the full adder has to sit there and twiddle its thumbs and do absolutely nothing before the carry-in comes? Or can it do some of the work so that when the carry-in comes, the amount of work left to be done is as small as possible? And the answer is that there is some of the work that can be done beforehand so that when finally that chain comes by, the amount of work left to do is as small as possible. So there's preparatory work that we can do. And in general, what we're going to do is we're going to shift the problem from being one of generating the sum and the carry out to being one of first deciding how to treat the carry. There's really two cases that we need to think about here. One is if I'm adding together numbers and I have one particular bit, if the carry were to come by, would I want to continue to propagate it further on in the chain? Well, when's that going to be true? I'm going to want to propagate the carry when? If it's 0 and 1 and a carry comes in, should I propagate the carry out? Yes. 1 comes in and a 0 and 1, should I propagate? 1 plus 1 is 0. Yeah, okay, so that's one case. Obviously, if a 1 and a 0 comes in and a 1 comes in, then I want to propagate out. What about the 1 and the 1 case? If a 1 comes in, should I propagate the carry out? Yeah, okay, so there's three cases. And the only one left is 0 and 0. And do I propagate then? Hopefully not, right? If a 1 comes in, then I eat it up and I spit it out here, but I don't propagate it out the output. So here I propagate, propagate, propagate. Okay. Second question. If, independent of what the carry in is, let's say I don't worry about that. I only worry about these bits here. In which cases, assuming that the propagation is handled in a separate way, in which cases here do I generate a carry, irrespective of what comes in? Here, no. Here, no. Here, no. Here, yes. Okay. So here I generate, and in those three cases I propagate. Now this decision, do I generate or do I propagate, is a decision that can be made beforehand, before the carry comes in. And first of all, the generate, you can even take action on before the propagate comes in, because it doesn't matter what the carry in is, in this case, you just generate the carry. And in the propagate case, you can get all the work done and all set up, so you're just waiting for this last bit to come in, which is a slow bit that's going down the chain, saying, okay, if I have two 1s, or if I have a 1 and a 0 or a 1 and a 0 here, if I have more than 1, 1, I get all set up waiting for the propagate to happen. And so I change the description of these things as follows. The carry out bit. If the generate bit is a 1, then I go ahead and I say I'm going to generate a carry over here. And I'll explain why these are x's in just a second. If the propagate bit is a 1, then I'm going to go ahead and if the carry in is a 1, I'll propagate the answer. And if the carry in is a 0, I will not propagate the answer. In other words, I'll propagate C sub I to the output here. This is C sub O as a function of C sub I. So in the case when P is high, I'll generate a 1 here and a 0 here. In the case when G is high, I'll generate a 1 here and a 1 here. I'm going to make a small change from what I just did on the board, just there. And I'm going to say that in the case when we're sure that we generate, let's not say that that's propagating. okay? Because it's really not that we're going to propagate the carry in that case. We're just going to generate the carry in that case. So I'll go ahead and say that propagate is going to handle these two cases of input. Generate will handle that case. And in this case, we don't propagate and we don't generate. So in this case, C sub O equals 0. In this case, C sub O equals 1. And in these two cases, C sub O equals C sub I. Great. Okay? Nice. So it will not be the case that generate and propagate are ever on at the same time, and that's the reason for the x's here, because we're saying that in the generate case, when A is high and B is high, we're going to turn the propagate off. So we're going to pre-compute G and P, and then based on G and P, we're then going to compute C sub O as a function of C sub I. And notice that this function is simple. This function just says, if propagate is high, C sub O equals C sub I. If generate is high, C sub O equals 1. Otherwise, it's 0. Very simple function. Okay? If G is high, 1. If P is high, take C sub I. How about the sum bits? Well, let's take a look. It's exactly the same as before, except that if the generate and propagate are off, then the sum depends on C sub I, 0 and 1. If we're going to generate a carry, but we're not going to propagate a carry, then what are the inputs? The inputs are both high. If the inputs are both high, then what is the output going to be as a function of the carry that comes in? A and B are both high, so we're summing together 1 and 1. And the question is, when a carry comes in, what's the output? The sum of 1 plus 1 plus 1 is 1. Sum plus 1 plus 1 and 0 is 0. So the output is equal to C sub I if both of the inputs are 1. So in the case when we've decided beforehand in our pre-processing, notice the G's and the P's do not depend on C sub I. But once we've figured out that we're in the G case, because both of the inputs are 1, if the carry comes in, then the sum is equal to the carry that comes in. So therefore, over here, if G is high, and notice these two cases never happen, if G is high, then sum is equal to carry in. Okay. When is sum not equal to carry in? Well, when we're in the propagate case, which is going to be this one over here. Because remember, again, this combination never takes place. If one of the things is a 1 and the other one is a 0, what does it mean? It means that if a carry comes in, then the output will be 0. If the carry comes in as 0, the output will be 1. In other words, it'll be the opposite of the carry that comes in. Okay, good. In the propagate case, the output is the opposite of C sub I. This is a simple function. What is this function? It's propagate XOR C sub I. That's all this function is, right? If propagate is true, then we want to invert C sub I. If propagate is not true, then the sum is equal to C sub I. So it's just P XOR C sub I. How about here? This is a simple function. If G is true, the output's 1. Because remember, it only happens here. It's never the case that we have both of them. So it's G or P and C sub I. That's a simple function too. So we've reduced the computation that depends on C sub I to two very, very easy things. And it looks like this. Okay? We have a preprocessor to generate G. Generate. If A is true and B is true, then generate the carry. If A is true, XOR B, and again, this computation takes place before C sub in comes in. Pre-processing that's done, then we're going to propagate the carry. Okay? And we set these things up so that the generate, if this is true, this is false. Okay? Because when we generate, we don't really propagate, we just generate. We're sort of blind. Okay? Okay, once you have G and P, then you just say that C sub out, like I just said, is G or P C sub in. Either the generate is true or the propagate is true and C sub in. And this function can be done very, very fast, faster than the computation we had before for propagating the carry chain. And then the sum can be done in the same way, like I just said. Just take P, XOR C sub n, and you get the sum. Two simple functions, a lot of pre-processing being done beforehand. So this will speed things up, and it's a great idea. That's what we've done over here on the left. But guess what? It turns out that we can do a lot more than just this. We can look ahead. We can look ahead and we can say, you know what? I'm going to have a sum bit and a carry bit that depends on whether these two things, say, generate or propagate. But I can actually design some parallel logic here, and I can break this chain, and I can look ahead of the logic down here and say, in certain cases, when this thing generates and this thing propagates, and this thing generates or this thing propagates, I can actually figure out what function I should use in order to create the sum and the carry out of this stage, and I thus break this link here by looking ahead for what the carry might be. And remember, all of these actions occur in parallel at the same time, so if I'm willing to expend some extra hardware over here, I can look ahead at G and P from lower stages to see whether or not I should actually do it. Now, what am I really doing here? Guess what I'm doing, guys? I'm getting closer and closer to the first slide that I had, which was let's implement an adder with a table of 2 to the 70 inputs. Because if I take this to an extreme, let's say this is the high order bit, bit 31, I'm looking at all the generates and propagates of all the lower bits, and I end up with some big messy function here saying I want to figure out real fast what the output is. And remember, the table could figure out things very fast, but then we kind of jumped to this extremely slow way of doing it. This is somewhere in between. Okay, I have somewhat complex functions over here that are looking at G and P of different inputs in low order bit stages. Now let's get back to this. I think this is where we're going to end. How does this thing work? Oh my God, it looks complicated. But guess what, guys? It's not complicated. Let's see how this might work. First of all, the carry input C from lower order stages comes in here and goes up here, all the way up here. And if you look at it, the first stage over here seems to only kind of have a few inputs here, and some of them are AND gates and some of them are XOR gates. The next stage is looking at more bits, and the next stage is looking at more bits, and the next stage is looking at even more bits. And furthermore, whenever we take A and B, we do a little work on them, and guess what? We generate 2 outputs before we feed them to the next stage. There's a line right here where every bit creates 2 outputs, where every bit of A and B is recoded to create 2 outputs, where bit 2 of A and B is recoded identically to each stage. Every stage is the same. Guess what the recoding is here between A sub 1, B sub 1, and the mystery wires right here. The mystery wires are G and P. Okay? And if you go through the logic here, now what fools you a little bit is that this ALU doesn't only add. Okay? In fact, this ALU has 4 bits, S0, S1, S2, and S3, that go down over here, all the way down here, and that plug into all these gates, and they allow it to do add, subtract, and or all kinds of fun things. And it turns out that if I just fix this code with the code for add, what you would find is that the G and the P that gets generated by the logic function right here, and notice this is a sum of products form. Here's the OR gates, here's the AND gates, here's the NOT, right? Okay. Each of these things will in fact be the generator for doing G and P. Now, how do we generate the sum bits that come out? Well, we seem to be taking some kind of an XOR, here's an XOR gate of G and P, and XORing it with a little bit of other stuff, and then there it comes out. Again, the same kind of thing here, XOR coming out, XOR going out, XOR of G and P that go out, and that's the sum bits. The carry bits, however, okay, are generated by logic, which seems to grow with each one of the stages. And the reason that it grows is that the generate for the next stage is taking a look at all the propagates and generates of the previous stages that we have here. So this stage here is looking ahead to this stage and to this stage and to this stage here. We go from least significant bit to most significant bit at the top, and it's peeking ahead at the generate and propagate from the less significant stages in order to do all of these functions in parallel at the same time. And that's exactly how that thing works.
And you can extend this to 32 bits without it going insane?
Well, it gets really big at 32 bits. So do you know what you do? You actually build a tree of generate and propagate things. It's not quite as fast as if you kept on broadening that out more and more up to 32 bits, but it can be faster. Let me talk a little bit about how fast things can get. How fast can an adder get? Well, you know, ultimately, that if you're adding two numbers, A and B, that ultimately the answer in any given bit may depend on all the bits of the inputs, somehow, right? Now, if you have gates like the huge OR gate that I talked about in the sum of products form, where you have a gate like this of, you know, a gazillion inputs, then sure, you can do it in a very small number of stages. You know that you can do any function in 3 stages of inversion, of ANDs, and an OR, okay? So theoretically, if this is 1/billionth of a second, and this is 1/billionth of a second, and this is 1/billionth of a second, it should only take at most 3/billionths of a second to do any function. But I'm telling you that's not true. And the reason it's not true is that if you put 2 to the 30 wires on here, it's no longer 1/billionth of a second. It's now, you know, 100 seconds, okay, or something awful. Okay, so infinite fan-in is not a valid abstraction. Fan-in is a measure of how many wires come into a gate. What's more reasonable is to say that there's finite fan-in. So this can get to, at most, let's say 10 wires. Okay, but no more. Well, you know that no matter how you do it, ultimately, if you have n wires as the input here, and let's say n over 2 wires as the output, that for certain combinations of the input, any given bit here may depend on all of the bits here. And the only way to get from here to there is with, you know, to the 1 bit here. So let's talk about the 1 bit of the n over 2. So how do I get from 1 bit here, from, you know, n, where n is a big number, how do I get from here to there with a set of gates, each of which has a finite amount of fan-in? In other words, input number of wires can't grow beyond a certain size. The only way to do it is to build some type of tree. And I don't know what the tree is going to be, but ultimately I have to do that because I need to make that bit sensitive to all of the bits here. And what does that mean? What's the order of growth of the speed of a circuit like this if each element has constant time? The bits come in here, they take constant time to go to here, constant time here, constant time here. So the height of the tree is equal to how long the circuit takes to work, which if this is n and the number of inputs is fixed and bound at some number, let's say 10, then it's order log n. So you cannot theoretically build an adder of a big number of numbers n, a big number of bits, any faster than order log n, as n gets big. Okay. But it turns out that n is usually not that big. 64, 128, it's not 10,000 bits. Okay, and so what that means is that usually the constant factors of the design will dominate what you in fact do. So it's basically order log n in theory, but in practice there's all kinds of tricks that you can do. I showed you the look ahead of generate and propagate. There's also other tricks where you pre-process the inputs and you change what base they're in. We've been only doing things in base 2. Well, what if we changed it to base 4 and operated in base 4? It turns out that you can actually build a faster adder if you do things in base 4 or in base 10 even, okay? Usually they don't go higher than 10, but this thing of recoding to a different base is something that is commonly done in high-performance adders that you see in the real high-end chips. And you're still up against order log n if n is big, but the constant factor can go down. Recoding to more bits always means that the amount of hardware you dedicate to doing the add begins to grow very, very big, okay? But the speed can go up. Yeah.
Does that mean having hardware that's sensitive to multiple levels of voltage or something?
One can't, well, that is yet another way to do it, okay?
Well, how else
So-
would you encode something other than binary?
Okay, so this is kind of an advanced topic that most grad students take classes in. I think the Hennessy and Patterson book may talk about recoding the radix of a number in order to make multiplies faster. They may not talk about adds being faster. But there's a graduate topic in architecture that I teach some of the time, that some other folks teach, that goes into n different ways to do this, and recoding is one of the ways. And you sort of, I don't know what the right way to say this is, but think about it that we're using, let's see what is the right way to say this here. What if you group the bits, okay? So here's, a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, okay? Rather than treating each one of these bits the way we've been doing now, treat them as little groups. So here's a number between 0 and 3. Here's a number between 0 and 3. And instead of adding this bit with bit b sub 0 and b sub 1, we're going to add the number between 0 and 3 to another number between 0 and 3. Worst case, we'll put it into a lookup table, okay? There's 2 bits here, there's 2 bits here. We can do this pretty fast, and we can get, two bits out here that's a little bit faster. But it turns out that it's complicated, okay? And so I kind of don't want to kind of spin off doing that stuff. But just be aware that recoding to a different base is a common thing to do. What you were talking about, which is where you don't actually use the binary system intrinsically in the hardware. So what we're going to be talking about in this class is how the binary system will be encoded in a voltage between a low voltage for a 0 and a high for a 1. Actually, some of the time we'll do it the other way around, but that doesn't matter for now. What matters is that there will be 2 of them. It turns out that you could actually encode more possibilities in a voltage range. So you could, for instance, say 0 volts is a 0, 1 volt is a 1, 2 volts is a 2, and 3 volts is a 3. And every wire can now take 2 bits of data, being a number between 0 and 3. Okay? And you can kind of do more and more of that to, in the limit, having what's called an analog computer. And of course, there you don't have any digital system at all, but you have just a voltage meaning what the number is. And to add 2 voltages to each other, you use an amplifier. Okay, what's called a summing amplifier or an op-amp. Okay, and you sum the voltages and you get a sum out. There's a nice way, if I wanted to know what the length of this piece of chalk is summed with this length of this piece of chalk, I have 2 ways to do it. I can measure this piece of chalk and write it out in bits. I can measure this one and write it out in bits, and I can add the bits together, right? Or I can put the 2 of them on top of each other and I can measure this, right? This would be an analog computing way of finding out what is the sum of these 2 lengths of 2 pieces of chalk. And so one scheme that you could use is you could have something called a digital to analog converter, or a D to A, which would take a number of bits in here and produce a voltage out here, which would correspond to how long this piece of chalk is. And so here's A that goes in here, and here's a voltage that corresponds to A. And then I could have another digital to analog converter here that would take B and produce a voltage corresponding to B. Okay, and then I could put it into an analog device to sum them, which is similar to putting the 2 pieces of chalk right on top of each other. And then after I got an analog voltage, which was the result, I could put it into an A to D converter, and I could get the sum of A plus B. And don't laugh, because people have actually built this. Okay? What you have to worry about is the conversion is never perfect. Sometimes the piece of chalk, it's a cold day, so the piece of chalk is a little shorter. Hot day, the piece of chalk is a little longer. The summer screws up a little bit. there's a thunderstorm outside, wham, a little bit of noise there, someone goes and pokes a circuit, and all of a sudden your bank account has a number in it which is different than it used to, okay? Because you took out $1, but it actually took out $1.05, okay? So in general, people don't do this sort of thing. Okay? So watch out for noise. Parallel computing, again, is a way of making things faster, and we began to get a little bit of a hint as to how to do that. Either the crazy example of a lookup table with 2 to the 70 entries in it, or looking ahead to the G and P bits more and more and more. But again, you have to watch out for cost, because the more you do this look ahead, the more hardware there is in order to do it. And then the final question, which I'll leave you with, is what about pipelined computing? Some of you, let me have a show of hands. How many people have heard of this term, pipeline? Okay, so around half. So the question is, what's a pipeline what is a pipeline computer? And of course the answer is that you're going to find out real soon, because around half of this course is going to be talking about how to make a computer faster by pipelining. And just to give you a hint as to what that is, who said that we had to do all the bits at the same time? In other words, if we thought of the 32 bits of an add as 32 steps in the assembly line of building a car, right? Who says that one guy has to build the whole car, and then when he's done, he has to go back and build the next car? Why can't we have 32 guys, each one engaged in building a particular part of the car, and any given car is spread over the line, so that while it takes one car 32 steps to make it through, the rate at which the cars are produced is 1 every cycle, okay? And if you can get your head around what I just said, what I'm kind of saying here is, even if we had the dumb adder, okay, where there's a sequence of steps to be done from the least significant bit to the most significant bit, we could do it like an assembly line and break it up into stations and have a little, man doing the adding here. Not paid very well, as usual, right? Actually, it's what my dad used to do. He used to put tires on cars. Said, someday my son will go to MIT. He actually did pretty well, too, but this was his first job. And the idea here is that the add for a given number proceeds through the line in stages. And while one add is having bit number 20 done, so here's add, A plus B, and it's the add number K. The next one is having bit number 19 done, and that's A plus B, but it's a different A and a different B, and it's number L. Okay, and so each one of them is going to march through. And so we will pipeline. The same total amount of work is done, but notice that these guys don't have to wait until the entire line is finished before the next one gets put in. And that's the whole key to why an assembly line works, is that you don't have to wait until one car makes it through the whole way before you start feeding in the parts for the next car. When we do our wash, right, we got the washer and the dryer, we don't wait until one load of wash is all the way through before we feed the next load of wash in. As soon as it's in the dryer, we put the next load. That's actually in the lecture that talks about this, because students do wash a lot. So, okay, that's it for today. Summary is right here, how we built the ALU, the trade-offs, the K-maps, and if you have time, and I'm not sure whether or not, there was a question as to whether or not this was going to be done, but in recitation you may talk about this. If not, it's totally optional, okay, because it's a lot of work, and I decided that we're going too fast. So, but it is in the textbook that you have, and you can look at that.